Friends, welcome back to my YouTube channel. In this class, I am going to discuss about the exergy of a flowing fluid, or you can say exergy of an open system. I am going to discuss. In the last class, I have derived an expression for the exergy of a closed system. Before starting, I must say one thing to all of you. Please do subscribe to this channel and of course like it and share it to your friends. Let's get started. You know, Exergy is nothing but part of energy, that is energy possessed by a system that that is available for conversion into useful energy. The maximum useful energy that can be derived from a system is called the available energy and or exergy. 100% of energy associated with a system can't be converted into useful work. So this is some portion is actually possible to be converted to useful work. So in the last class, I derived an expression for exergy of a closed system. So to अगर हम ये ओपन सिस्टम का एक्सर्जी निकालना चाहते हैं तो फर्स्ट वी हैव टू नो व्हाट इज द एडिशनल एनर्जी that is contained in an open system or flow stream in comparison with the closed system. Closed system में जो energy रहता है, what is the additional form of energy that is associated with a flowing fluid or an open system, or you can say control volume, and that additional energy is nothing but this flow energy. Flow energy is nothing but the energy is nothing but the energy needed to maintain flow in a pipe or duct. एक सेक्शन जो अपस्ट्रीम में है वो डाउनस्ट्रीम का फ्लूइड को धकेलेंगे सो दैट देयर विल बी ए फ्लो मेंटेन्ड. So that is the flow energy, and this is the only form of energy which is available in case of an open system and not available in case of closed system. So अगर हम ये जो flow energy का एक्सर्जी निकाल देंगे और इसको हम ऐड कर देंगे जो expression we have derived for the exergy of a closed system, so we will be able to find out the exergy of a flow stream. So बाकी का सब चीज़ तो सेम है. Only thing we have to find out the exergy associated with this flow energy. Flow energy is nothing but pressure multiplied by specific volume at a section, where this small b stands for volume change of unit mass of fluid as it is displaced during flow. अपस्ट्रीम फ्लूइड जब डाउनस्ट्रीम फ्लूइड को पुश करेंगे तो ये डिस्प्लेस हो जाएगा वो फ्लूइड. सो उसका जो चेंज इन वॉल्यूम आएगा पर यूनिट मास, दैट मीन्स स्पेसिफिक वॉल्यूम, when multiplied with the pressure available at that section is known as flow energy. So अगर हम एनालिसिस करेंगे, सपोज दिस इज योर पिस्टन सिलेंडर अरेंजमेंट लेके Actually, there is no piston. This is an imaginary piston acting here in case of an open system. Suppose this is an imaginary piston which is analogous to your downstream fluid only. So सपोज ये बाउंड्री है, इसके अंदर सपोज फ्लूइड है जिसका प्रेशर है P एंड स्पेसिफिक वॉल्यूम है स्मॉल v. There is a shaft associated with it also. एंड ये जो P0 एग्जर्ट हो रहा है, दिस इज द P0 इज द प्रेशर एग्जर्टेड बाय सराउंडिंग ऑन दिस imaginary piston, and this imaginary piston is nothing but this is an imaginary piston. जैसे कि पिस्टन सिलेंडर अरेंजमेंट में होता है क्लोज सिस्टम में, बट दिस डज नॉट एग्जिस्ट हियर, बट फॉर एनालिसिस पॉइंट ऑफ व्यू वी हैव अज्यूम दैट दिस इज एन इमेजिनरी पिस्टन, एंड दिस इमेजिनरी पिस्टन रिप्रेजेंट्स द फ्लूइड डाउनस्ट्रीम. क्योंकि ये अपस्ट्रीम फ्लूइड है, दिस पुशेस दिस डाउनस्ट्रीम फ्लूइड, सो इट कैन बी कंसिडर्ड or it can be analyzed as an imaginary piston, and this is the pressure exerted by this exerted by surrounding or atmosphere on this downstream fluid or imaginary piston. And this P0 is acting in the opposite direction and this pressure is acting in this direction. So flow energy जो PV है, what is the exergy of this flow energy? Exergy of this flow energy will be PV minus P0V, where P is the pressure exerted by this fluid at the upstream side, and P0 is the pressure exerted by atmosphere, which is actually acting in the opposite direction. Why this is like this? Because whatever energy is given to a fluid in the form of flow energy, all that energy is not, that means whatever energy is given by the upstream fluid to the downstream fluid, that is your imaginary piston, all of that cannot be converted into useful work in the form of piston displacement work. Here जो वर्क शाफ्ट वर्क प्रोड्यूस हो रहा है, वो शाफ्ट वर्क is not equal to P multiplied V. This shaft work is actually equal to P multiplied V small b minus P0 multiplied small b, because portion of this energy is used in pushing the surrounding. So that's why this minus this represents the useful shaft work, and this is the maximum useful work that can be extracted from this flow energy, and this is the exergy associated with the flow energy P multiplied small v. Actually flow energy है P multiplied v, but exergy of this flow energy will be PV multiplied by PV minus P0 v, where P is the pressure exerted by upstream fluid on the imaginary piston or downstream fluid, and P0 is the atmospheric pressure exerted on this downstream fluid, or you can say the imaginary piston. So अगर हम ये फ्लो एनर्जी का एक्सर्जी निकाल सकते हैं, दिस इज द एक्सर्जी एसोसिएटेड विद द शाफ्ट वर्क इज नथिंग बट एक्सर्जी ऑफ फ्लो वर्क, एक्सर्जी ऑफ फ्लो वर्क, or you can say flow energy also. And you know flow energy is associated with a flowing fluid only, and this is not available in case of a closed system, and in closed system only the piston displacement work is there. So exergy of flow work is PV minus P0V, where P0 is the atmospheric pressure. So whatever expression we have derived in case of a closed system, we will add this exergy only to that to find out the exergy of a flowing fluid or exergy of a flow stream. So you know exergy of flow, mathematically you can express it like this: exergy of associated with the flowing fluid or flow process is actually this is exergy of flowing fluid is equal to exergy of non-flowing fluid plus exergy of flow. Exergy of flow, actually this is flow work. In exergy of flow work, we have just calculated, and that is PV minus P0V. And exergy of non-flowing fluid, we have derived already an expression for exergy of a non-flowing fluid or closed system in the previous class. And that is equal to exergy of a non-flowing fluid per unit mass. We know that is nothing but U minus U0. The small u is the molecular internal energy, and U0 is the molecular internal energy possessed by the system at dead state. That means when the system comes in equilibrium with the surroundings, plus P0 multiplied by V minus B0. This expression we have already derived, minus T0 S minus S0, and all these properties with 0 subscript refers to that those of dead state. Dead state means when the system comes in equilibrium with the surroundings, plus of course kinetic energy and potential energy here are not neglected, they are taken into account. And this is the exergy associated with closed system, and we will add to this the exergy associated with flow energy, and that is P minus P0 multiplied by V. So यहाँ एक्सप्रेशन आ जाएगा U प्लस पी भी माइनस U0 प्लस P0 V0, यहाँ से आ जाएगा। और ये जो यहाँ से आ रहा है P0 मल्टीप्लाइड भी, यहाँ से माइनस P0 मल्टीप्लाइड भी विल कैंसल आउट. So now our expression is like this: minus T0 S minus S0 plus V square by 2 plus GZ, and these refer to the exergy of a flowing fluid per unit mass. Small u is specific energy, internal energy. So this is also specific entropy. So this becomes, U plus PV is nothing but H, enthalpy, specific enthalpy, H minus H0 minus T0 multiplied by S minus S0 plus V square by 2 plus GZ. So this is the exergy. This expression is the exergy of a unit mass of a flowing fluid in which we have taken into account the kinetic energy and potential energy. And most of the cases, these kinetic energy and potential energy terms are neglected. So it can be expressed in terms of a function called psi also. Psi is nothing but the exergy of a flowing stream of fluid, and this is H minus H0 minus T0 S minus S0. This is the availability function of an open of a flowing fluid only, and this is required while doing exergy analysis of a control volume. When we are going to apply exergy balance principle in case of a control volume or open system, this psi will come into picture, because this represents the exergy associated with the flowing stream. H minus H0 minus T0 multiplied by S minus S0 plus V square by 2 plus GZ. This is the exergy of a flowing fluid. This is nothing but exergy of a flowing fluid per unit mass, of course. And if you go into the energy of a unit mass of flowing fluid, we have already studied that in your earlier chapter while studying energy balance principle. Theta represents the energy per unit mass of flowing fluid, and this is nothing but H plus V square by 2 plus GZ, where H is the specific enthalpy of flowing fluid and V square by 2 is the specific kinetic energy and GZ is the specific potential energy. Out of this term will be deducted, so that exergy of a flowing stream will definitely be less than theta. Theta always represents the energy per unit mass of a flowing fluid, H plus V square by 2 plus GZ. अगर हम चेंज इन एक्सर्जी निकालेंगे, सो एक्सर्जी चेंज निकालेंगे, तो एक्सर्जी चेंज ऑफ ए फ्लूइड स्ट्रीम, एक्सर्जी चेंज ऑफ ए फ्लूइड स्ट्रीम as suppose ये एक process, when it undergoes a process from state 1 to state 2, what will be the exergy change of a fluid stream? अगर हम निकालना चाहते हैं तो as it undergoes a process from state 1 to state 2, that will be delta psi will be, suppose एक जो flowing fluid undergoes a state change from initial state to final state, as it happens in case of a steady flow device or unsteady flow device. So wherever it undergoes a process between some two states, initial and final states, so change in exergy will be delta psi will be psi 2 minus psi 1, and this will be, psi 2 will be H2 minus H0 minus T0 S2 minus S0 plus B2 square by 2 plus GZ2. This expression is for psi 2, and for psi 1 this will be H1 minus H0 minus T0. This is 0. This is 0. So T0 S1 minus S0 plus V1 square by 2 plus GZ2, and if you calculate this will come out as S2 minus H1 minus T0 S2 minus S1 plus V2 square minus V1 square by 2 plus G multiplied by Z2 minus Z1. अगर हम काइनेटिक एनर्जी और पोटेंशियल एनर्जी को नेग्लेक्ट कर देंगे तो these two terms will drop out from this expression. But this is the expression for change in exergy of a flowing fluid when it undergoes a process from state 1 to state 2, and H2 is the enthalpy of the specific enthalpy of the fluid at state 2. H1 refers to the specific enthalpy of the fluid at state 1. Similarly, S2 and S1 represents the specific entropy of the fluid at state 2 and state 1 respectively. So this is the expression. That's all.